Welcome back. We're here in the fourth video, fourth lesson of solutions unit. In this part, we're going to be talking about concentration and how we can measure concentration, putting an actual number to this term. And so we're going to start by using molarity. But let's just start broad picture here. Concentration is a proportion of the amount of stuff dissolved to the amount of stuff that it is dissolved into. So it's a ratio. How much stuff, solute, is in how much stuff, solvent, water. So what we do here for the Regents is we use the molarity formula. What you will do if you want to right now, you can go check your table T of your reference table, and you will find this formula there. It says exactly this: moles of solute over liters of solution. Now it'll come up later, but the liters portion is really super important. So what we got here is some math. Okay, but it is important for us to also just know that when it comes to molarity, the smaller the molarity number is, like 2 versus 3, the smaller the number is, the less concentrated it happens to be. All right, so just keep that in your mind. But basically, we want to know the total number of moles for how much liquid it is dissolved into. So the first two examples that we're going to look at using this formula, big M equals moles over liters. The first two examples are really, really straightforward and simple. So you'll see. How many moles of NaCl are required to make a 2-liter solution if the concentration is 0.5 molarity? And so at this point, this is what I mean by this is a very simple question, because it's literally just plug and calculate, as long as you plug things into the right places. So we have our big molarity here. Big M is molarity. So 0.50 molarity is equal to, I'm looking for moles, so I don't know what this is, and it's divided by liters, which I've been given in this question to be 2.0 liters. So basically your moles would be, if you're more comfortable with an X, that's where your X would go. And we're just going to solve for X by doing 0.5 times 2, coming up with an answer for this question of 1 mole. Right, so a 0.5 solution, molar solution, that is 2 liters big, must have 1 mole of solute in there. The one thing I want to point out is this doesn't matter. Doesn't matter at all. This situation of 1 mole of any solute in 2 liters of solution would have this concentration of 0.5. Okay, so the solute doesn't matter when we're talking about concentration. Similarly, here's another simple version of this question with one extra step. So molarity equals moles over liters. What is the molarity of 100 milliliters if it has 0.5 moles? So it's simple in the sense that we're just plugging stuff in. Right? So we know we're looking for big M. That's molarity. We know that we have 0.5 moles. That's our numerator. The denominator has to be in liters. And since we're given milliliters, we have to do a quick conversion. For those of you new, to convert from milliliters to liters is a division of 1,000. Right? There are 1,000 milliliters in 1 liter. So if we move our decimal place 3 spaces, we would be left with 0.1, and that is 100 milliliters expressed as liters. And so that's what we would get. Now we do this math, which is 0.5 divided by 0.1, and we would find out the molarity of this solution is a 5 molar solution. So again, in the last question, these simple ones, I said the solute doesn't matter, to the point where this question doesn't even talk about the solute. It doesn't mention what it is, but it tells you that you have 0.5 moles of it, and you have 100 milliliters of it. So the molarity is 5. Okay, those are the simple versions of this question. They get a little bit more complicated when we start adding grams. Right? Because the truth is, you can't make a solution in a lab using just moles. You can't measure moles without measuring grams. So these next three get a little bit more involved. Brings back a little bit of review too. First part of this question, as I've separated, is the simple part. Right? How many moles of HCl are required for 50 milliliters of a 6 molar solution? So 6 molar is equal to the moles, which we don't know, over liters. So again, 50.0 milliliters is not liters. So we'll move our decimal place 1, 2, 3 spots, and then we can rewrite this new number as liters. So this is simple, this is easy. We can figure out the number of moles the exact same way we were doing it before, 6 times 0.05. Now what we get is 0.3. The unit that is involved with that is moles. And so to this point of the question, we've answered it. But the second part of the question, which I'll underline and I'll do in blue, right? This part requires a little bit of review, some old stuff. So on table T, if you recall, there is a mole calculation formula. And that says that the number of moles is equal to the given mass, which I hate. I don't like that it's written as given mass over the gram formula mass. All right, and we're going to use this formula for the second part of this question. Now, what do we know? What do we have from this, what we've already done? We do already know that our number of moles is 0.3. What we do not have is a given mass. See, that's why I don't like the term given mass. And what we don't know at the moment is gram formula mass. But what we do know is that the molecular formula is HCl. And think back, think back, think back. If we take the mass of one hydrogen and add it to the mass of one chlorine, we are going to get the gram formula mass. And let's do that. Right? So according to the reference table, hydrogen has a mass of 1.0, and we only have one, so we only need to include one. The mass of chlorine is 35.5 when it's rounded. So for this formula, the gram formula mass would be 36.5 grams per mole. Now we have to do this extra step. We have to do this extra step in order for us to have two parts of the equation. We already have this, and now we have this. And so we can plug it in, and I will summarize all of this in one moment. All right, then we plug it all in. We have 0.3 moles from our first calculation. This is going to equal a given amount of mass. And we have a gram formula mass of 36.5 grams. So we do a little algebra, right? We do a little 0.3 times 36.5, and what we find out is some weird number of 10.95 grams. Now that's not got the right significant figures, right? It would actually be 11 point, nope, it would be 11. No, it would be 1.0, but that's neither here nor there. This number right here would be your final answer. And here's what that all means. Right, I'm going to try and make this make sense. If we put 10.95 grams of HCl into 50 milliliters of water, we would have a concentration of 6 molar. Another way to word that is, if we put 10.95 grams of HCl, we're really putting 0.3 moles of HCl into 50 milliliters of water, and therefore we would be left with a 6 molar solution. So this is the most complicated the Regents level will make molarity. I'm going to do one more of these just so that you, and I'm going to go a little bit quicker, but I'm going to do one more in the exact same way and show you exactly how this works. So it's a different solute. Now, when we're dealing with grams, a different solute is important. So the question says, how many moles of NaOH are needed to make 100 milliliters of this solution? That's the easy part of the question, right? I've broken this up into 2 parts, right? But this can clearly be merged into one. So let's do it step by step. The first question asks for how many moles. So how many moles? Well, I know that molarity is moles over liters. So I know that if I'm just taking the information from the question and plugging it in, it's a 2.5 molarity equals X amount of moles over 0.1 liter. I moved the decimal place in my head, so 100 milliliters is 0.1 liter. So 0.1 times 2.5 is 0.25. Right? So that means in this setup of any solute, we're dealing with 2.5 moles. But I want to know the grams. Now this part is where the solute actually is important. So if I needed to find out the number of grams, I'm going to use the second formula. The moles is equal to the given over the GFM. I have this, and since I have the formula, I can find this. And so we're going to do that. We're going to take 1 Na plus 1 O plus 1 H, and that will give us the gram formula mass. And so from our reference table, we would be dealing with 23.0, 16.0, and 1.0. This would be our gram formula mass. So 39, 40, 40.0 grams per mole. Now basically, if I knew I had 1 mole, it would be 40 grams. But I don't have 1 mole. I have 1/4 of a mole. So if I come back up to this formula and plug it in, it would be 0.25 moles equals X amount of mass over 40. And 40 times 0.25 would leave me with 10 grams. Right? So in summation, 10 grams of NaOH is 0.25 moles. And if I put 0.25 moles in 100 milliliters, I would have a 2.5 molar solution. All right, so I really hope that that clarifies a little bit about how molarity works. And it is the biggest one in concentration that is talked about and asked about. There are some others. They're much more simple. I'll hit those really quick, but you shouldn't need too much thought in this one. Okay, so the other 2 types of concentration calculations are called parts per million. It's this one right here. And in a minute, we'll be doing parts of mass and percent composition. This formula for parts per million is also on your reference table. Okay, go look at it now. Make sure you see it. Make sure I'm not lying to you. right? But the mass of the solute divided by the mass of the whole solution times a million is the calculation that we do for parts per million. So watch as I do one practice example, and you'll see how simple it really is. It's just kind of plug and chug, and you get an answer. The question is asking, what is the concentration? And what's nice is it tells you you're using parts per million, so you know you're using this formula. Of a solution would contain this much solute in this much solution. All right, so let's just do it. I'm going to use this formula right here. ppm equals the mass of the solute, what is dissolved. We're going to divide that by the total mass of the solution. Now, some of you might be thinking, well, this isn't a mass, it's a volume. Well, water has a density of 1, meaning its mass divided by its volume equals 1. So if its volume is 100, its mass has to be 100, right? Because 100 mass divided by 100 volume gives you the density of 1. So the mass and milliliters of water are identical numbers. Okay, 100 grams times 1 million. Punch it into the calculator. Beep, boop, beep, boop, beep, boop, beep. And what you would find out, there are 43 parts per million oxygen in this question. Parts per million is really useful for small amounts of stuff. A lot of it is used in pharmaceuticals or in environmental checks to make sure drinking water is safe, there's no poisons, and there are safe levels that it can be drinking, whether it's lead or mercury. And those numbers are so small that it's used, parts per million is the concentration typically used for things like that. The last concentration calculation is one that we've been doing for a while. Right? This particular formula is not on table T, but the formula that says the part over the whole times 100, the percent composition formula, that is on your reference table, and that is all this is talking about. The part is clearly always the solute. The whole thing is obviously the whole solution. So watch this. There is a little trick here that people get messed up on, so pay attention. What is the concentration of a solution where we're taking 50 grams of a solute and we're putting it into 100 grams of water? Okay, so we're taking 50 grams and we're putting it into 100 grams. What is the percent composition? Part over the whole. The part is simple. It's 50 grams of dissolved salt is my part. The whole thing is 50 plus 100. The whole thing has a mass of 150 grams. Right? Because the whole solution includes the solute and the solvent. And that's the part where people get messed up because they just want to plug in 100 and move on. Right? But it's part over the whole solution, and the whole solution is 150 times 100 equals 33%. Right, so I really hope that cleared up any questions that you might have on concentration, how to calculate it, the 3 different ways the Regents really hones in on. And I hope you stay tuned for the next one. We're going to talk about colligative properties, meaning what happens to a solution when we add salt. And make sure you please like the video, subscribe to the channel, right? Enjoy the rest of these videos. Thank you so much for watching.